Okay, number 16 asks us to find the inverse of a function. When we find the inverse, basically we take the x value and the y value and we swap them, and then we solve for that new y value. Remember that f of x is just another name for y. So right now this function is solved for y. If we are asked to find its inverse, we're going to swap those two variables. So we are instead going to have x equals y minus 3 to the fifth minus 2, and then we want to solve for that y value. So first step, let's move that 2 over to the left. Then we need to get rid of the exponent. So we are going to use a radical. Specifically, we're going to take the fifth root of each side of our equation. On the right, that fifth root and that exponent cancel each other out. So our final step to solve for y, we're going to add 3 to both sides. Now be careful when you rewrite this, okay? So we now have y equals the fifth root of x plus 2, and then the plus 3 is not under the radical. So make sure you give yourself a little space there. If you wanted to write the 3 in front, just to be safe, it's a positive 3 and a positive radical. So either one of these answers works for our inverse function. Okay, next up, another inverse, but this time we also want to talk about the domain and the range of our inverse function and our original function. So once again, we're going to swap the x's and the y's. So instead of y equals, we have x equals. Make sure you replace both of those x variables with y's. We have to swap every variable. We need to first get rid of this fraction. So we're going to multiply both sides by 2y minus 5. On the left, I'm going to go ahead and multiply that x. It's x times 2y and x times negative 5. On the right, they cancel. That's good. The fraction's gone. Keep in mind what we're trying to do. We are trying to solve for y. That means any term with a y must be on the same side of your equation. Any term without a y should be on the other side of your equation. So I'm going to gather all my y's over here on the left-hand side. So I'm going to add that 5x to move it away. And then I'm also going to subtract this 3y to bring it over. I want all the y's to be on the left. So when I do that, I can't combine those. Those aren't like terms. So I have 2xy minus 3y. These cancel. Equals, these cancel, 4 plus 5x. Hey, one step closer. The y's are all on one side. That's good. Now we have y in two separate terms. So in order to get it where we can solve for y, we're going to factor that y out front so that we have just the y in the one location. This is y times 2x minus 3. So to solve for y, we're going to divide by 2x minus 3. Cancel, cancel. And we have y. Or if we want to label it as our inverse, it would be f inverse of x equals 4 plus 5x over 2x minus 3. There is our inverse function. We do also want to talk about domain and range. So we'll go ahead. I like to make a little table to talk about those. If we're going to talk about domain of f of x and f inverse of x, and then range of each of those. So domain of our original function up here at the top, remember for a fraction, the bottom cannot be 0. So that's what we have to check on. We have to make sure that 2x minus 5 is not equal to 0. If that was equal to 0, it would be undefined. So I'll add 5 to both sides and then divide by 2. So the range for our original function would be all real numbers except 5/2. Then we also want to look at domain of our inverse function. So again, the bottom cannot be equal to 0 because that would be undefined. I'm going to add 3 to both sides. and divide by 2. So the domain for our inverse, again, all numbers are good except for 3/2, because that's what would give us that 0 in the denominator. Now remember, domain is the set of x values where our function is defined. Range is the set of y values where our function is defined. So because of the way that the function and the inverse function are related, the way we did that, we switch the x and y's. The domain for our original function, the x's, becomes the range for our inverse function, or the set of y's. Similarly, the domain from our inverse, the x's, becomes the range for the original function. So once you figure out those two domains, you also know your ranges. There we go. Number 18, we're looking at a quadratic function, and we want to put it into vertex form. We want to list our transformations, and then we want to graph it. So to put it in vertex form, you can do a complete the square. I like to just use the little vertex formula. H is negative b over 2a, and that's going to give us the x value of our vertex. For this problem, b is negative 6, and a is 3. Those two negatives knock each other out. We get 6 over 6, or 1. K is what we use to represent the y value of our vertex. And we find that by taking the answer we just got and plugging it into the function. So 3 times 1 squared minus 6 times 1 minus 4. That's 3 minus 6 minus 4, which is negative 7. So there is our vertex, the point 1, negative 7. That's going to be the most important point when we go to graph it. We're going to do that in a minute, but first we're going to work on this vertex form. We're going to write that out. So our vertex form would be f of x equals a. A is the same whether you're in vertex form or general form, so a is 3. X minus h, quantity squared. Don't forget to square it. If we don't square it, it's not a quadratic. And then plus k, we would have plus a negative 7 here. We would simplify that to simply minus 7. So there's our vertex form. Now that we have it in vertex form, we can talk about the transformations that are going on here. So this minus 1 in the parentheses, that is going to be a shift to the right by 1. That 3, it's a multiplier out front. That is going to be a vertical stretch. And that minus 7 at the bottom, that is going to be a shift down by 7. Now we already found our vertex, 1, negative 7. That should match with our transformations, right? When we have a parent function, our vertex is there at 0, 0. So I shift it to the right by 1 and down 7. And there it is. And that's what we found for our vertex, 1, negative 7. Those should go together. Now, sometimes students have a little trouble graphing transformations with a stretch. It definitely does make it a little trickier. If once you find that vertex, you have trouble with these transformations, we can use a few other clues to help us graph it. It's super easy to find the y-intercept of a quadratic equation right here. Remember, y-intercept is where x is equal to 0. So 3 times 0 squared minus 6 times 0 minus 4. 0 minus 4 is negative 4. So that's our y-intercept. So that's a nice point to be able to graph, 0 and negative 4. Because of our axis of symmetry, a quadratic, a parabola is symmetrical around the vertex. We also know automatically that we're going to have a point over here that matches that y-intercept. And then maybe we'd like to have one more point to graph. We've got x equals 1, x equals 2. What happens when x equals 3? You can plug that into either form of the equation that you like. 3 times 3 squared minus 6 times 3 minus 4. That's 27 minus 18 minus 4, which is 5. So that's another point on our parabola, x equals 3, y equals 5. 1, 2, 3. And again, because of that axis of symmetry, I know there's always got to be another point on the other side of the vertex, and that definitely gives us enough points to sketch out a nice parabola for our quadratic function. Number 19, we have a nice polynomial here. We want to find all values of x, where f of x is positive, f of x is negative, and we also want to sketch our graph of x. So we're going to start off here by talking about that leading coefficient test. Our leading term here is this one. It's got the highest exponent. It has specifically an odd exponent, and it is a positive term. So that tells us about the end behavior or the tails of our graph. If it's odd and positive, that means the tails are going to be going in opposite directions and kind of uphill from left to right for that positive. We have to figure out what's happening in between here, but we do know it's going to be down on the left and up on the right. After we figure that out, then we need our x-intercepts. So we are going to set that function equal to 0 and solve for x. To do that, we need to factor. And when we have 4 terms, what we typically want to try is factor by grouping. So these first 2 terms both share an x squared. And these last 2 terms, at first you might say, well, they don't share anything. But since this leading term in the second half is negative, I am going to factor out a -1. And what's left behind then is positive x plus 4. And that looks nice because now these two match. So that means my factoring by grouping is working. I pull that x plus 4 out front. And then what's left behind is x squared minus 1. And x squared minus 1 is the difference of 2 squares. So it factors one more time. And we get 3 x-intercepts. We get one at -4. We get one at +1. And we get one at -1. Notice that each one of these came from a factor which does not have an exponent or is raised to the first power. So each one of these has a multiplicity of 1. That odd multiplicity tells me that at every point, each time we are going to be crossing, not just touching or bouncing off, but crossing that x-axis. So let's plot those x-intercepts, -4 and +1 and -1. And then I sketch in my end behavior. I know it's got to be down to the left and up to the right. And then I already said I'm going to cross at each one of these points. So this one's just a nice little roller coaster. I go uphill, and then I got to hit that next x-intercept, and I go down, and then I have to hit that next x-intercept, and I go up again. And there's my graph. We do want to list our positive and negative intervals. Greater than 0, those are the positives, and less than 0, those would be the negatives. So our positive intervals are anything above the x-axis, so here and here. Remember, we use x values to show where those areas begin and end. This begins at x equals -4, and it stays above until -1. And then it is above again, starting at 1, and it stays up for the rest of the graph. We are negative here and here. Again, looking at our x values, that first green highlighted negative section is from -infinity up until x equals -4. Then it's above. We don't want that. We're looking for negative intervals this time. Then it goes under. It's negative again from -1 to +1. And number 20, exact same directions as number 19. Our polynomial is just in a little bit different form. So we're still going to follow the same procedures, but we'll talk through it. It'll be just a little bit different. Again, we want to find that leading, we want to do that leading coefficient test. So we're looking for the degree and the sign of our leading term. When it's factored, what we need to do is we need to consider each one of these factors. Notice this one has degree 3. That is an x cubed. So that's going to give us 3 towards our total degree. This one, x minus 5, is just to the first power. So that gives us 1 towards our total degree. And this one, x plus 3, that is squared. So that gives us 2. So 3 plus 1 plus 2, that is 6. So this one is going to be even degree. Make sure you add up the exponents from every factor. And notice our leading term here is negative, and these other x's are positive. So we're going to end up even and negative. Even means both tails go in the same direction. Negative means both tails are going to be pointing down. Then we want to find our x-intercepts. So we take that factored polynomial and set it equal to 0. It's nice when it's factored already, because then we just take each one of those factors and set them equal to 0. Negative, if we divide both sides by -1, we still get x cubed equals 0. If we take the cube root of both sides, we still get x equals 0. So there is one of our x-intercepts. This one has a multiplicity of 3, which is odd. So we are going to cross the axis at that point. Here we'll add 5 to both sides. There's our next x-intercept. This one has a multiplicity of 1, which is also odd. So we are going to cross at that point as well. This last one, if we take the square root of both sides, we get x plus 3 equals 0. Then subtract that 3. This one has a multiplicity of 2 because it was squared. And so this one is where we're going to have a touch. Okay, plot those x-intercepts. We have a 0 and a positive 5 and a -3. Put those tails on there. It's got to be down to the left and down to the right because of our even positive leading term. And then see what's going on with our multiplicity. We are touching or bouncing at x equals -3. So we're not going to cross through. We're going to go turn around and come back down. And then where do we go next? You always, once you do your cross or your touch, have to go to the next intercept. So we got to go up here. At 0, we're going to cross. And then we have to go to that next intercept. So we got to turn around and come back down. At 5, we're going to cross. And there's our graph. For our positive and negative intervals, greater than 0, those will be our positives. Less than 0, those will be our negatives. Oops, negative. Well, let's fix that. So positive, there's only one. It's this one right here. That's the only place our graph is above that x-axis. X values, that highlighted area begins at x equals 0 and ends at x equals 5. That's our only positive interval. All the other intervals are negative. We cannot just string them all together because it's strictly less than 0, not less than or equal to 0. So we do need to do it in pieces. It's below the x-axis from -infinity to -3. It is still below from -3 to 0. And then it's below again from 5 to infinity.